Good morning, everyone. This is Waseem Akhtar. I'm a PhD student in Professor Etho group. So today I'm going to talk about one of my PhD work, which is coherent state transfer between these hyperfine coupled photoexcited triplets and the 29 nuclear spins in silicon. Basically, this work is giving 29 nuclear spin quantum memory in silicon. So, which I will explain subsequently in my slides later. This work has been done in collaboration with our Oxford group under Professor John Morton and one of his PhD student, Vasilia Frido, and Professor Leonard Velasenko. So to begin with, I will just give you a brief motivation for this work. So the motivation is that we all know that there have been lots of quantum computer models ever since the Keynes quantum computer model was proposed. So one such model was given by our group, which is like all silicon quantum computer model, where we used 29 nuclear spins as a quantum memory. It has been proposed, and to read out this 29 nuclear spins, it was proposed that a phosphorus electron spins would be used to read out the nuclear spin states in the silicon. But in this work, I'm going to give an alternative. I'm giving an experimental demonstration to manipulate these 29 nuclear spins and to read out the nuclear spin state using photoexcited triplet state in silicon. And the other one thing which we all know is that there have been lots of electron spin qubits and nuclear spin qubits, which the electron spin or the nuclear spin can be used as a qubit for quantum computing. But there are some merits and demerits with electron spins and nuclear spins. For example, the electron spins, though it have very high thermal polarization, can be achieved at working experimental conditions, and it is fast to manipulate. But then there are lots of interaction with the environment in the lattice, which dephases the electron spins very fast. Whereas the nuclear spins, these are very isolated, and so it has very long coherence times. But then these are very low in thermal polarization at experimental conditions and very slow to manipulate. So the way forward for achieving quantum computing, or the feasibility of quantum computing, is to merge these two, the electron spins and the nuclear spins. They couple this electron and the nuclear spins, and then we use electron spins are used for calculations, and then the nuclear spins will act as a memory because it has very high long coherence times, because as it is very isolated systems in the solid state. So with this brief motivations that we want to study a couple electron spins and a nuclear spin system in silicon. And the important thing is that there have been such study in diamond, where NV centers, which we all know is a very good candidate for quantum computing, but it has been proposed recently that the hyperfine coupling of the NV centers with the nearest neighbor, the 13 carbon isotopes in diamond, which has been used as a couple hybrid systems, like electron spins coupled to a nuclear spins. When we say an electron spins coupled to a nuclear spins, we will have this Zeeman energy splittings, where where this state corresponds to an electron spin up and then nuclear spin up, and this space corresponds to electron spin down and the nuclear spin up, and subsequently for these two states. And it was shown in the works that the electron coherence here generated here can be transferred to the nuclear coherence, and there was a long coherence time of 13 carbon was studied using this coupled systems. But in this work we are going to talk about 29 nuclear spins in silicon. This is again a stable isotope in silicon, and which has got very long coherence time, 25 seconds has been proposed. And the added advantage is a well-developed silicon technology, as well as isotopic engineering for 29 silicons. So with this brief motivations, I will just give introductions to what kind of centers I am talking about in this work. Basically, I am going to talk about a photoexcited triplets coupled to 29 nuclear spins, and so how we can manipulate these 29 nuclear spins using these photoexcited triplets. So this photoexcited triplets, which I am going to talk in this work, is about the oxygen vacancy centers in silicon. These oxygen vacancy centers are basically created when we gamma irradiate our samples with or by neutron irradiations or electron beam irradiations of CZ grown silicon. Under irradiations, we break the bond here between these 4 silicon atoms. The 2 silicon atoms bridge by trapping oxygen, and these 2 silicon atoms will be left with lone pair of electrons. Now this lone pair of electrons will form bonding and anti-bonding orbitals, and under ground state we will have that these 2 electrons here will be in a singlet state, which we say as a ground state of the defect. Now when we illuminate our sample with light, then when we illuminate our sample, we create hole and electrons, and these electrons get trapped by this ground singlet states of the defect and get transferred to the triplet state. And under application of magnetic field, this triplets splits into these states, and then these triplets are as metastable states, and so they will again decay back to the ground singlet state via spin orbit coupling. So and these are the decay rates which I have marked as K plus, K0 and K minus for different states, triplet states. Now these centers are basically anisotropic centers, and they have different orientations in silicon crystal. So but in this work I'm just going to talk about two of the main orientations, which I say as SL10 and SL190. The SL10 is one in which when the magnetic field, applied magnetic field that is parallel to 110, and the radius r joining the 2 silicon atoms connected by a vacancy, if these 2 are parallel here, when the magnetic field is along 110 direction, we say the center has to be SL10 center. But when the magnetic field B and the vector r connecting the 2 silicon atoms having a vacancy is perpendicular, we say as SL190 orientations. So this is basically the triplet centers which I'm going to talk about in this work. So with these brief introductions to the triplets, let me come to the results and discussions part. So the results and discussion is that this is basically a pulse EPR study of the triplets, which has been done in Bruca spectrometer, and we for photoexcitation we use a pulse laser which is 1064 nanometer wavelength, and sample was like a CZ grown natural silicon samples, which was irradiated with 1 mega electron volt electron beam at the dose of 10 to the power 8 per centimeter square. So to begin with, I will just give eco-detected EPR spectrum and then try to figure out the decay kinetics of this triplet spins, and then subsequently show you the coherent transfer experiments. So this is the eco-detected EPR spectrum where we apply a laser pulse, and then we create centers, triplets in our sample, and then measure the Hahn-Eco the Hahn-Eco sequence. We measure the eco intensity as a function of magnetic field. We scan the magnetic field and measure the eco intensity as a function of magnetic field. So this is what we get. This is basically matches very well with the previously reported CW EPR spectrum of these centers. Now you see the satellite peaks here. This satellite peaks shows very strong hyperfine coupling with 29 nuclear spins. So the 29 nuclear spins, which is situated very near to the vacancy here. We have a vacancy here, oxygen this. So very near to the vacancy. The nearest neighbor is the hyperfine coupling of this strength is from coupling to these 29 nuclear spins, which is very close to the vacancy here. So in presence of these 29 nuclear spins, so our states look something like this. And here I have shown the decay rates K plus, which go to the ground singlet states. So basically this is the whole energy levels which is relevant in this work. So now I will try to characterize these decay rates for different levels using this two well documented pulse sequences, which one is called flash delay and inversion recovery pulse sequence. The flash delay is that we measure the eco intensity as a function of delay from the laser after the laser pulse. And in inversion recovery, just after laser pulse, we apply a pi pulse and then measure the echo intensity as a function of this waiting time here. So these are the two spectrum which we get for different lines. I'm talking about these 4 lines. It corresponds to these 4 lines here, and I'm showing you the flash delay and the inversion recovery spectrum, and you can see that the flash delay and the inversion recovery are more or less identical, which shows that just after the laser pulse, the population in all the states are more or less equal. All the 3 triplet states are more or less equal just after the laser pulse. And this decay kinetics didn't show any variation within the temperature range of like for T less than 20 Kelvin, less than or equal to 20 Kelvin. So we say that there is no contribution of spin lattice relaxation within the spin levels. I mean the triplet levels. So to model that, we just use this decay model where we say that after laser pulse we equally populate all the levels, and then they decay back to the ground singlet state using with these rates, and then the population difference as a function of time can be given as by a bi-exponential factor, something like this. And when we fit our bi-exponential equations to the flash delay curves, we will get a bi-exponential for the flash delay curves. We will get the various time constants for various states. For example, for SL10, K0 is like 2 milliseconds. The time constant is like 2 millisecond lifetime, and plus 1 state is nearly 284 microseconds. So you see that one of the state is decaying very fast, and the other one is long-lived. So as a result of which, we can have a polarization buildup, non-equilibrium polarization buildup in the system. So this is what I show here, that how does the polarization changes between 2 spin levels as a function of waiting time. So you see that we can get within 1 millisecond, we can achieve nearly 100%, more or less 100% polarized system in our sample, which is like a very, very well initialized spin system. And later I will show that we transfer this well initialized spin systems to the nuclear spins, and then manipulate those nuclear spins, and then transfer the coherence back to the electron spins to demonstrate the quantum 29 silicon quantum memory. And to confirm our decay model, we just measure 2D spectrum, 2D analysis of this sample as a function of, like, we apply a laser pulse and then wait for a time t, and then apply a pi pulse and then wait for another time t, which we say y, and then measure the echo intensity as a function of x and y here. So, and I simulated it on the basis of my decay model which I have used, and very close correlation between these two says that the decay model perfectly describes the kinetics of the triplet, and our assumptions that the triplet that there is no relaxation, T1 relaxation within the spin energy levels is consistent with this. So till now we have already characterized the lifetimes of the triplets and shown that we can achieve nearly very high spin polarization in the spin system, in the triplet spin system. Now let me go to the coherent transfer experiments. So as we know, as I've shown you earlier, that 29 nuclear spins, which is very strongly hyperfine coupled with the triplets. So we can have something like this spin levels in our system. So I will show you that we can transfer the electron coherence which is generated here, can be transferred to the 29 nuclear spins coherence here. So to do so, first we need to know what is the exact energy levels here. I mean, what is the exact energy, and then to figure out that, we try to measure the endospectra first, and then subsequently I will show you the Rabi oscillations and the coherent transfers. So this is the to measure the endospectra, I use the Davis endo pulse sequence, and which is described as we apply a laser pulse, and then these are the pulse sequences. So now what we do is that we know that this is the energy levels which we are talking, and as we have already shown that T0 state has a smaller lifetime as compared to the T+1 state. So what happens that after a laser pulse, when we wait for time t, we wait long enough so that all the t naught has decayed, and we just get populations in the t+1 levels. So we have a very high polarized system here. Now what we do is that we apply a pi microwave pulse between the electron levels here. So when we apply pi pulse, we flip the electron from here to here, populations from here to here. So now we have a very high polarized spin systems in these levels, as compared to this, where there was no polarization here. Only the polarization was in the electron spin levels, but after application of pi pulse here, we have created a polarization in this spin levels as well, between the nuclear spin states as well. Now what we do is that we scan our RF frequency. So now the RF frequency is scanned, and we measure the echo intensity in this level, which we hear, as a function of this RF frequency. So when this RF frequency matches exactly the energy splitting here, then we can transfer completely the population from this state to this state, and the echo intensity will go to 0 because of the same population. So we can see a curve for endo. We can achieve an endo spectrum as a function of this RF frequency. So here is the for one of the state, I'm showing that we measure the endo spectrum here. So it is we can see nearly 122 megahertz of this splitting corresponds to nearly 122 megahertz, and such a strong hyperfine coupling distinguishes these nuclear spins from basically in our sample we have lots of nuclear spins also in the lattice, but the one which is very close to the vacancy is strongly hyperfine coupled, and so it can be distinguished from the rest of the environment in the sample, and so we can easily address this 29 nuclear spins using these photoexcited triplets. Now to measure the coherent manipulation of this 29 nuclear spins, we use a pulse sequence something like this, where we again apply a laser pulse and create wait for time t to create our electron polarizations, and then measure the echo intensity as a function of, we fix the RF frequency now to 122 megahertz, which we have got from the Endor experiment, and then we measure the echo intensity as a function of pulse width of this RF to 122 megahertz RF. So as a function of pulse width, we can just we get a Rabi oscillation here, which demonstrate that we were able to manipulate this 29 nuclear spins via this photoexcited triplets in our sample. Now I've demonstrated two things, that Endor spectrum and as well as the coherent manipulations of this nuclear spins. Now I want to show you the coherent transfer, which subsequently means the quantum memory of 29 nuclear spins in silicon. So this is a well used pulse sequence by Professor John Morton at Oxford University, and the pulse sequence is something that we initially create a electron coherence. For example, if we are considering this energy levels, then we create a electron coherence, and then by using this pi microwave, we refocus this electron coherence, and then using successive RF and microwave pi pulse, we transfer this electron coherence to the nuclear coherence here, and then again refocus this nuclear coherence, and then with this pulse we transfer the nuclear coherence back to the electron coherence and measure echo intensity, and the echo intensity as a function of this waiting time tau n here will give you this plot, and fitting gives nearly a time of nearly 0.8 milliseconds. And you see that this 0.8 millisecond is very close to the lifetime of this triplet state. We are creating nuclear coherence here, so this is very close to the lifetime here. So this nuclear coherence is basically limited by the lifetime of these triplets. So this is not the intrinsic nuclear coherence time which we are measuring. So it is affected by the decay of the triplets to the ground singlet state. So to measure the intrinsic coherence time, what we do is that we apply a bit different pulse sequence, and the sequence is that we fix our experimental length, so that the experimental time interval was fixed to nearly 1 millisecond, so that any effect of the decay we can remove that effect, because those things which are affecting, the decay of the triplets affecting the nuclear coherence. So what we do is that we again initialize our spin system after initial laser pulse, and then this pi RF will create pi by 2 RF will create a nuclear coherence, which is refocused by pi by 2, and then again by second pi by 2 RF pulse we transfer the nuclear coherence back to the electron coherence, and which is measured as a function of, which is measured by Hahn-Eco sequence here. So here what we see is that this eco intensity as a function of this, as we scan this waiting time between pi by 2 RF and pi RF, as a function of that, it looks like more or less it does not decay much, but anyway it is very much scattered. And when we fit this red line, which gives you nearly a time constant of 5 milliseconds with large uncertainty in this 5 milliseconds. But anyway, the thing which should be focused is that 5 milliseconds is much greater than the lifetime of the triplets, which initially in the previous slide I showed that it was nearly 0.87 milliseconds the nuclear coherence time, but now we are getting nearly 5 milliseconds of coherence times. So this 5 millisecond coherence times, in order to explain that, it was shown much earlier that in one of the paper in JJAP, that the 29 nuclear spins measured using a Hahn-Eco sequence give a decay, a very fast bi-exponential decay in the eco intensity, and they have shown that nearly 20 millisecond initial very fast 20 millisecond decay, and then have a slow 200 milliseconds decay time. So we feel that this decay which we are getting here could corresponds to this 20 milliseconds, because this has a very large uncertainty here. So we expect that it could correspond to this 20 milliseconds, and this 20 millisecond was basically limited by the dipolar interactions between the nuclear spins in the lattice. So we have shown that we can achieve much higher, much longer, and it is possible that in future we can achieve much longer nuclear coherence times by using some different pulse sequences. So let me conclude the thing. So it was shown that the flash delay and inversion recovery experiments, that we have different decay rates for the electronic spins, and then we can achieve nearly 100% polarization within the triplet sublevels. And I demonstrated a coherent manipulation of 29 nuclear spins using these triplets, and then subsequently we show that the transfer of quantum information between the electron and the nuclear spins. So we were successful in demonstrating the 29 nuclear spin quantum memory in silicon. Thank you for your kind attention.